Okay, let's take a look. What's my length? How long is it? 15. So then what's my height of my rectangle? 1 over 15. Remember, it doesn't have to start at 0. Right? My length is only 15. What's the probability they'll arrive in 20 to 25 minutes? Here's my 20-ish. Here's my 25-ish. How long is it from 20 to 25? 5. And how tall is it? 1/15. So 5 times 1/15. 1/3. Great. Good. Questions? Need a minute with each other? All right. So now we get to the hard part. This is one of the harder concepts. It is the hardest concept of this exam. So for the next 5 minutes, you guys really need to focus. If you focus really hard and pay attention the next 5 minutes, then you're going to be okay. If not, you're going to be totally lost and confused. So totally need everybody with me the next 5 minutes. Now, I'm waiting for a bus that comes every 20 minutes. My expected wait time is 10 minutes, right? However, if I take a sample of 30 people, right, and how long each of them waits for the bus, random sample of 30 people, how long they waited, how long she waited, how long he waited, average them up. My average of these 30 people won't necessarily be exactly 10 minutes, right? It might be 11.24 or 9.43, right? Does everybody understand what I'm saying? I expect it to be 10, but it's probably going to be, it probably is going to be a little bit off of that. So imagine I take a whole bunch of samples. I take a sample of 30 and find the average. Find all their sample means, all their X bars. So every one of these represents a sample of 30 and their average. So this one is a sample of 30, the average of a sample of 30. This is another average of a different sample of 30. Here's another sample of 30 and its average. So these each represent 30 and the average of them. Does everybody understand what I'm saying? So every one of these is a mean, an average of 30, a sample of 30. All right. The central limit theorem says that these sample means are going to be normally distributed. That means that they're going to be centered around 10, around the mean. Most of them are going to be there, and then they're going to be fewer and fewer the further and further away you get. Forms a normal distribution, which is super cool. We call that the sampling distribution of sample means. And we're going to talk about some of the nifty things about them. So the first thing is, if I take a sample of 30, my average wait time is 10 minutes. Take a sample of 30, what do I expect to get? The mean? 10 minutes, right? I expect my sample should be right around 10. All these samples should be right around 10. So the mean of these samples are also 10. That totally makes sense. We expect them to be all right around 10. So my sample mean, in other words, my mean of the sample means, my mu x bar. Do you see a little x bar there next to the mu? That means that's a label. That means the mu of the x bars of the sample means. Sample means being all these sample, take the mean, sample, take a mean, sample, take a mean. The mean of all those is going to be whatever your regular mean is. Because we expect all those to be whatever the mean is. But the standard deviation of the sample means, sigma x bar, is going to be the regular standard deviation divided by the square root of n. It's going to be smaller. We'll talk in a minute about why that is. But first, make sure we're clear. You should be filling in your notes on this, right? It's in your notes. If I take 10 minutes on average is how long people should wait for the bus. If I take a sample of 30 people, I expect that average to be right around 10. If I take a bunch of those samples, I expect all their averages to be right around 10. They should be centered at 10. And as you get further away from 10, there should be fewer and fewer of them. Their mean is the same as the regular mean, 10. But their standard deviation, sigma x bar, is going to be the regular sigma divided by square root of n. It's going to be smaller. This is why. You guys remember Steph Curry in 2016? That was the year he was hitting three-pointers all over the place. He had like 2 or 3 50-point games. That was also the game where that was also the season where in the last 3 seconds he took the ball in at halfway court and did this and just from almost halfway and got that three-pointer right at the end. Right, you guys remember that? Okay. Yeah. So he averaged 30 points a game. It wasn't necessary. It's right for him to have a 50-point game. It was right on the borderline of unusual. Right? It could happen. It's not crazy. We're on that borderline of what you consider unusual for him, right? So I might say that his standard deviation is about 10. Okay. So not unusual for him to, if I randomly pick one game of his, it would not necessarily be all that unusual for me to pick a 50-point game. However, if I randomly picked 25 of his games and averaged those 25 games, am I going to get an average of 50 points? No, not even close. Right? There is no way, because I can't pick all 50-point games. Even if I pick 2 games, the odds of me picking both 50-point games is really slim. Right? It's going to be, because for every 50-point game I pick, I'm going to most likely pick I could randomly pick a 10-point game. Right? They're going to kind of cancel each other out and be closer to his average of 30. So what we're saying is, because when you pick a big sample, there's a lot of canceling out that goes on. The big ones kind of get canceled out by some of the small ones. And the larger sample you take, the more often you're going to have this canceling going out, that there's going to be a balance. Then my range is going to be right in here, not way out here. This red thing is for one game. One game totally could get a 10-point game, or I could randomly pick a 50-point game if I'm just looking at one game. I could get anywhere along here. Most of the games are in here, but I totally can get a game out here or out here. But if I pick 25 of them and average them, I'm not going to get that. They're all going to be a lot closer to home, a lot closer right in here. The standard deviation is going to be a lot smaller. It's only going to range this much, not this much. So the standard deviation is going to be, well, let's see. My sigma x bar is going to be my standard deviation over square root of n. What's my standard deviation? 10, I said. And this is for 25 games, so my n is 25. What's the square root of 25? 5. So I'll get 2. My sigma x bar, if I average 25 games, it's going to be a lot more like this, right in here. You guys want to stare at this for a minute with your neighbors?
Yeah.
This is the tough concept, so go ahead and take a minute and talk about it.
Will, on the homework and the exam, will it be, they'll give us the standard deviation just
Yep.
in the corner, and then we just...
Yeah. So remember, anytime we're talking about normal distribution, I have to give you the mean and standard deviation. I have to. Those are the 2 things I have to give you, always.
Okay.
Yeah.
Wait, so what's the tricky part about this?
Oh, all right, so there isn't a tricky part about this. And that was, just the idea is the tricky part.
Okay.
There's a couple of rules about it. One is, if the original variable is not normal, like that uniform distribution we just saw, then you need to have a sample size of at least 30 or more. in order for this normal thing to kind of happen. If the original variable is normally distributed, then it doesn't matter. You can have any sample size because it's already normal. Right, and that kind of makes sense because if my n is 1, sigma over the square root of n, what's the square root of n? What's the square root of 1? 1. Sigma over 1 is just itself, so it would have the same standard deviation. It wouldn't change at all. All right, so you guys do problem 7 on your lab. So, in other words, find sigma x, mu x bar, and find sigma x bar. Find those two things. All right, so our mu x bar is just what? Just mu. So what is that? 86. Our sigma x bar is sigma over square root of n, which is 8 over square root of 24, which you guys said was what? 1.63. 63? Okay, sounds good. That works. Great. Now, why is it useful? One really useful way is if we take a sample, we can find the probability that a mean when the sample will fall in a certain range, regardless of whether or not it's normally distributed. Here's the deal. We love normally distributed because we have a really nice definition. It's symmetric. We know all the probabilities of being within this range or that range or from here to here. We can find, if you give me 2 z-scores, I can find the probability of being between those 2 z-scores. Normal is really well known. It's really easy for me to calculate. But a lot of distributions out there, a lot of random things we want to know about are not normally distributed. So we don't know how to figure out how it matches up with the rest of the world. If we take a sample of 30 or more, that is normally distributed. And I can see if our thing is unusual or not. So a lot of what we're looking for is to try to figure out if our thing is unusual or not. And we don't know if it's, typically if it's more than 2 standard deviations away from the mean, it's unusual, right? With normal distributions. So you can kind of see if your sample is unusual or not with a normal distribution. So that's what makes this really valuable for statisticians, is that they don't have to only use distributions that happen to be normally distributed, which there aren't a lot necessarily. So here is an example. Rosa, go ahead and read.
C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the age of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours.
Great. So, bless you. So here, let's see the things that are really important to us. So the first thing, let's see, between the ages of 2 and 5, that's just a detail about the children you're picking, like the 1.5 ounce bar of chocolate, right? It's a descriptor. But here we get to an average of 25 hours. What's that? Mu, average. That's my mu. Assume the variable is normally distributed, we need that. And the standard deviation is 3 hours. Ooh, standard deviation is 3. So that's my sigma. Good. If 20 children are selected between the ages of 2 and 5, if 20 children between the ages of 2 and 5 are randomly selected, what's that? 20 randomly selected. That's my n. Whenever you see the word randomly selected, or chosen, or surveyed, that's your n. 20 were surveyed. That's my n. A survey of 20. A sample of 20. The selection of 20, right? That's your n. The next thing is find the probability that okay, so here's it. Finding the probability. What are we finding the probability of? Find the probability of what? That the mean. Whenever you're looking at the probability of a mean, that should be your first clue. Normally, we find the probability of a number, right? Like with our chocolate bar, find the probability that a chocolate bar will be between these things. The one we did earlier was just one chocolate bar. Now we're talking about the probability of the mean of a bunch of chocolate bars, or in this case, a bunch of hours, a bunch of children will be greater than 26.3. So this is 26.3. The mean is 26.3. That's not an x, that's an x bar. So you need to keep straight the difference between an x and an x bar. An x is just 1. If I'm just finding out if one mouse has a standard deviation of blah, 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 or has a height of this, or if I'm talking about one candy bar. But here, I'm talking about a mean of a bunch of them. Taking a sample of a bunch of them, and their mean is something. That's an x bar. The other hint is our chocolate bars. What was the n? There was no n. Do you guys see what I'm saying? If it has an n, then that means it probably has a mean of that n, a sample, an x bar. Do you guys understand what I'm saying? Once you're taking an n, then n's is a sample, right? A sample of size n, you're going to have an x bar. You know what I'm talking about? So that first one, see what it says an average of 25 hours? That's not a sample. That's out there in the world, everybody. Average of 25 hours. That's my mu. This is a sample. A sample has a mean. That's an x bar. Those are totally different, and you need to keep track of which one's which. Does everybody get it? Do you guys have a handle on that one? Mm-hmm. The sample mean. You have a sample, that mean, that's your x bar. Just the general average, no samples associated with it, like the top one. Children between the ages of 2 and 5 watch an average 25 hours. Is that a sample? No, it's not a sample. That's just a regular mu. Okay, so once you have this x bar, then you'll be thinking, oh, I've got to use, I've got to use this sigma x bar. That's a sigma x bar problem. So that's how you figure out it's a central limit problem, and that you need to use sigma, why is this going? Sigma x bar. Those are your Q's. This means those two things, the n and the x bar, are telling you that you need to use sigma x bar instead of sigma. So how does this work out? Let's see. Well, first of all, I don't like the way they drew this picture because I think we shouldn't have that. So I need to find 3 over square root of 20, which is, let's see, .671. Okay. So now I'm going to take a look and say, all right, I have my x bar. I need to find a probability. I need to find the z-score for it. So I'm going to find my z-score, which is going to be my x bar minus my mu. But because I'm using x bar instead of x, instead of using sigma, I'm going to use sigma x bar. So that's where this comes into play, and that's all that matters. So Joey, when you're talking about why does this matter, or where does it come into play, the only place it comes into play is instead of using sigma here, I'm going to use sigma x bar. So instead of this being 3, it's going to be 0.671. And that's all that's the only time that's where which is a big difference, right? But that's the one step that changes. Instead of using sigma 3, I'm going to use sigma x bar, 0.671. Why? Because I'm taking a sample. And when you take a big sample, your data is not going to be spread out like this. With Steph Curry, it's going to be like this, very small spread. So I'm gonna have 26.3 minus my mean, 25, divided by my sigma x bar, 0.61, 6.671, sorry. So I think it ends up being 1.94. Okay, and then the rest of it's exactly the same as we've been doing, exactly the same. I have a z-score, I draw a picture, put a notch in the middle where my middle is, and then 1.94, it's somewhere on the right side, 1.94. And do I want less than this or greater than this? I want greater than. Do you guys see this part here? Probably it's greater than. So I'm going to go with this side over here. Which means that my other z-score will be way out here, positive infinity. And I'm going to do normal CDF of 1.94, comma, some large number, 221. Why not? Large number. Any large number. And if I do that, I will get, oh, why don't I just do this? It's easier. I will get 0.0262. Right, second VARS, normal CDF, 1.94, comma. Yep. Okay, you guys ready to do your problem? Okay, so go ahead and work on, is it lab problem 8? The one at the very bottom of the page. And there's the answer, which we missed the explanation of, but there's your sigma x bar and everything else. So now I'm going to show you guys the project.